Good morning, friends. So far we have in this course soil and water conservation studied what is soil erosion, its type, causes, effects, and also we have tried to find the solution control of soil erosion through agronomic or structural measures. And after that we have also studied about the land capability classification, how we can adopt different soil and water conservation measures to control soil erosion. Today the topic that we will be dealing with is how do we estimate and how do we measure the soil loss. In other words, how to quantify the soil loss in terms of volume, in terms of the average annual soil loss happening in any area per hectare. See, the topic today is soil loss estimation and measurement. There is basic difference between measurement and estimation. When we talk about measurement, we actually go to the field and measure the actual amount of things happening. In this case, soil loss, we can go and measure the soil loss. And when we say estimation, then some empirical formulas are used, either through field experimental study or through lab studies or through some mathematical or simulation modeling. Such type of measurement or determination is called your estimation. Talking about measurement, soil loss can be measured. There are many methodologies to measure the soil loss in the actual field. There are, in the subsequent lectures or classes, we'll come to know about runoff simulators, and also there are runoff plots from where experimentally through field experiment we can measure what is the actual amount of soil loss that is taking in a particular field. Also, there is a technique which is used in many water conservation structures like water harvesting structures and also in any minor irrigation projects. There, how do we measure the soil loss? Because soil loss is even very important as far as the capacity of the pond or the water retaining structure is concerned, because due to soil loss there is a deposition of silts on the beds of the soil, thereby it reduces the overall capacity of your dam or your pond or lake. As a result, there can be frequent flooding, inundation or flooding of the nearby areas. So to understand the soil loss from that particular catchment, catchment is an area from where rainfall or runoff comes and converge and contribute in that pond or the lake. So in such type of structures, what we do is we construct a pakka sedimentation tank or lined sedimentation tank, cemented sedimentation tank of rectangular shape. So when the water or the runoff overland flows, when there is excess rainfall, the excess runoff will pass through the sedimentation tank, and after that only it will go to the inlet of your water harvesting structure. So what will happen? The turbulent water which is coming as a result of runoff, it will first go to the sedimentation tank. It has got a certain depth, maybe 1.52 meters. So it will get deposited there. Then after that it overflows into the tank or your dam. So here the turbulent water, that water is is allowed to settle down. That's why we call it desilting basin. So once it is settled, the heavier particles or the sediments get deposited on the bed of the tank, and this, when dried, we can take out the entire sediments or the sand, and it is carried out manually and its weight is measured, and this mass or weight of that sediments can be extrapolated to the soil loss from the catchment area. This is how you measure the soil loss from a particular area through sedimentation tank. And more practical method is, we call it the wooden peg method. Here what we do is we insert a wooden peg of cylindrical shape into the soil of any catchment area, of any area which is prone to soil erosion or soil losses. We insert it to certain depth so that the outer surface of the soil is, the top surface of the soil is at the wood surface, and we mark it with some ink. We will mark it. Say suppose this is the soil bed, and the soil depth is up to, top surface is up to here, and this wooden peg is inserted and kept there for over a long period. Maybe after 10 years, come again measure. If there is change in the soil profile, then this will, if there is erosion, frequent erosion taking place, the soil surface come here, maybe 1 centimeter, 2 centimeter over a period of, long period of 5, 10, 15, 20 years. So if this is 1 centimeter, we can convert the soil loss in terms of tons per hectare. How do we convert it? Say in a certain place, if through wooden peg method, we have we determine that soil loss is 1 centimeter, and we have taking the reading after 10 years. That means in 10 years, 1 centimeter of depth or 10 mm of depth is depleted due to soil erosion. Now this 10 mm will correspond to 1 mm per year, because it is happening over a period of 10 years, right? So it is 1 mm per year, and it can be per unit area also. Maybe we take it 1 mm per hectare. Now we can quantify it in terms of volume. How do we quantify it? 1 mm is 1 by 1000 meter, and 1 hectare is 10,000 square meters. So 1 by 1000 into 10,000, that is 10 cubic meter of water of soil is getting depleted. That is, the soil loss in that particular area is of the tune of 10 cubic meter. We are taking easier units so that the calculation can be easier for explanation. It could be 15 mm, it could be 20 mm, it could be even 5 mm also. So in this case, if 1 mm of soil is depleted over a period of 1 year from 1 hectare of land, we can also convert this in terms of volume. It has come out to be 10 cubic meter per year per hectare. Now you can also change it in terms of mass or mass. How? By, if we know the bulk density of the soil, supposingly the place under consideration is sandy type, and sandy type of soil is having a bulk density around more or less 1.5 gram per cubic centimeter. If it gets converted into kg terms, it is 1500 kg per cubic meter. So how much volume of soil we have got is being eroded in this particular case where we are explaining, it is 10 cubic meter. So if we convert in terms of mass, it would be 10 into 1500, that is 15,000 kg per hectare per year is the annual soil loss, and that corresponds to 15 ton per hectare. So what I mean to say is, we can even have a rough idea about, through this peg method, we can actually measure, not estimate mind you, we can measure the soil loss for an extended period of time. So in this example, we have got it as 15 ton per hectare per year. Now second is the estimation. Estimation is based on the premises of many factors. This soil loss estimation, there is a very popular equation in soil and water conservation, which we call it universal soil loss equation, or USLE. This was devised by two field workers, Wishmer and Smith, in 1958. And this universal soil loss equation is estimated for rill and sheet erosion in agricultural fields, and it is done through in a specified land under specified field conditions. That everything is very much specified in this, the length of the field as well as the slope of the field, the crop that is grown, or the management factor which we are adopting in this particular field. It is specified under controlled condition. This USLE is derived, and it is a very popular predicting model or formula for estimating the soil loss from a particular area. And this is very popular too, and even now it is extensively used, and this formula is used for derivation of many other formulas as well. What this universal soil loss equation says is, this soil erosion, if we see, we have understood the factors affecting the soil erosion. This is a function of climate, it's also a function of soil, it is a function of topography, and also it is a function of land use. By land use we mean how the land is being used. Is it for agriculture? If it is for agriculture, it is in the mild slope area, or is it for a particular set of crops, or is it for a particular case of bushes. So the factors which affect the soil erosion, based upon these 3 or 4 factors, this universal soil loss equation has been derived, which is given by A is equal to RKLSCP. A is equal to RKLSCP. You have noticed I have underlined this term LS. Why I have underlined it, I will tell you later. This R is, here A is the annual soil loss in ton per hectare, and R is the rainfall erosivity index, which is expressed in megajoule mm per hectare hour. This R is the function of rainfall, is the intrinsic property or capability of the rainfall to erode the soil. It is deals with the kinetic energy of the this rainfall. We have also discussed in raindrop erosion the impact of rainfall on the soil surface. We have discussed. Similarly, this R is the function or the property of the rainfall or its intrinsic capability to erode the land. And K, which is given by in terms of ton hectare hour per hectare megajoule mm. This is defined as the property of the soil to resist the impact of this R. That is the property of the soil to resist the rainfall erosivity. So one is action, other one is reaction. In more colloquial way we can say it. And this L is length of the slope. What do we mean by length of the slope? Length, if we have a certain length of a certain gradient, the total length through which the rainfall or the flow of water has to pass, we mean length of slope by that. And S is the steepness of slope. So that means how steep the land is in terms of degree or in terms of percentage slope. So this factor, this LS, this is unitless. We take the combined effect of L and S. That's why I have underlined this LS, and whenever we use this formula, this in RKLSCP, this LS is a combined factor. Of course, the value, its value is determined from some table which I will be explaining you. And C is the crop management factor. Crop management factor, by crop management factor means how what is the land use of that place and which different types of crops we have grown. And let me tell you one more thing. This RKLSCP is particularly for agricultural land. It's not for non-agricultural land, because we do not consider the gully erosion here. It is, we consider only the sheet and raindrop and your gully rill erosion. So this crop management factor is the agronomical management, how well the particular land is managed or covered with crop. This is the factor. If there is no crop, barren land, this factor will be 1. And P is the conservation practice factor. Conservation practice factor, as we have already studied in land capability classification, if the particular land, if any conservation practice is adopted like contour farming, strip cropping, bunding or terracing, then this factor value will change. If there is no conservation practice, it will be 1, value will be 1. So since this A is directly proportional to all these components RK, L, S, Cp, anything if value of LS, Cp is less, that means the rate of soil erosion according to this estimation would be less. So it would always be desirable to have less value for P, less value for C, less value for LSCP, and R and K, it's not in our control because rain that is falling, we don't have any control. The intrinsic property of the soil, the erodibility or the capacity of the soil to resist the impact of rainfall, that also more or less we do not have control. Some control we might have through some manipulation of the soil or some amendments, but most of it R and K we do not have any control. So in a properly conserved land, this LS CP can be managed. Even the L and S also the control is less, but this C and P is something which is under our control and through which we can reduce the impact of soil erosion. Now coming to each term, what is rainfall erosivity? As we have already discussed, it is the function or the intrinsic capacity of the rainfall to cause erosion, and it is a product of kinetic energy of the rainfall and also the maximum 30-minute intensity. Through some Wesmer, the scientist Wesmer, through his study, he found that for this estimation I30, that is the maximum 30-minute intensity of rainfall during that duration, is sufficient for estimation of this rainfall erosivity. So according to this equation, R is EI30, that is energy into intensity, maximum 30-minute intensity of the rainfall, that is the kinetic energy into I30, where K is the kinetic energy, I30 is the maximum 30-minute rainfall intensity during the storm, and this is obtained, this I30 is obtained through the rain gauge data. So this data should be available with you so to know this R value. Second is the soil erodibility index or the K. This is the, we have already discussed this, resistance which is offered by the soil parent body to both detachment and transportation. What is soil erosion? Detachment, transportation and deposition of soil particles from one place to another. So here this is the resistance offered by soil to resist the impact of rainfall erosivity. And this equation is based on the premise that a standard runoff plot is constructed. The length of the plot is 22.13 meter and the slope of the plot is 9%. In terms of degree, it is 5.16 degree. And this plot is kept fallow. There is no cultivation. It's kept fallow and it is tilled up and down the slope, not across the slope. To make the purpose of this is to simulate a situation in the field where there can be maximum possibility of soil erosion. They have kept a considerable slope. If the slope is high, the erosion will be high. surface flow will be high, as a result the erosion will be high. If the length of the slope is long, so more amount of water will be, more amount of soil will be collected, will be carried away through erosion. So here they have kept a standard plot length of 22.13, plot slope of 9%, and have kept the that plot fallow without any crop and clear of any vegetation, and the tillage operation which is done is again which encourages erosion, that is up and down the slope. We have studied in the agronomic measure, if we plow up and down the slope, the erosion will be more. If we plow across the slope, then it will offer resistance through ridges and furrow. And here the LS, C and P is kept at 1, that is maximum possibility of erosion. C, that means there is no crop cover. P, there is no conservation practices. And LS, you know, this combined effect of plot length and land slope, this factor, this can be determined through a table. Here, therefore, the soil loss in this case is a function of only R and K, that is rainfall erosivity and soil erodibility. From the known value of of R, if we have a rainfall of certain or storm of a certain magnitude, and we can determine the soil loss, and K can be estimated. Hence, we can find out we can estimate the total soil loss happening in this runoff plot, standard runoff plots, using this universal soil loss equation. Second important factor is the topographic factor. This is the combined effect of L, length of slope, and steepness of slope, that is LS. The standard length, as we have discussed in the previous slide, is 22.13, and steepness of the slope is 9% or 5.16 degree to normal to horizontal. And this LS factor is mathematically derived by this formula, where L by 22.13, where L is the length of, we can simulate it for other type of field condition. So this is 22.13, and this L is the length of the slope, for which we have to determine the LH factor. Say, suppose we have to find the LS for a particular area which has length of slope as 200 meter. Then this 200 meter will come here, and this is the 22.13 is the standard, standard length of slope, and M is a exponential factor by this sin squared theta plus 4.58 sin theta plus 0.065. This is an empirical relation, theoretical relation, through which we can find the value of L and S. This theta is the angle of the slope, and if we have to find the LS for any particular field under question, then we have to find what is the slope of that place and what angle does it make. Slope and angle both are different. Say something will have slope of 100%, but its angle would be 45 degree only. So if this exponential factor M is 0.5 for slope greater than 5%, 0.4 if it is 3 to 5%, and 0.2 for slopes less than 3%. And through this we can find through this mathematical equation we can find the combined effect of LS, that is the topographic factor. There's Morgan in 2005 has conducted a trial experiment where different slope length and different steepness, they found the LS value like this, 18.3, and it came from 7.6 to 18.3 for this type of data, for slope length of 10, 70, 100, 140, 90, and steepness as 36, 25, etc. They have found out this. For practical purpose, you can have your own slope length, you can measure your own steepness, then you can find the LS factor. And more easier, in a more easier way, someone has explained, if this is for high mountainous area where we can have LS very high. In such places, the soil erosion will be very high. So for normal agricultural field, you will have gradient like 0.5, 1, 2, 3, 4, up to 10, 15. And for 50 meter, the value of, this is in feet, we have to convert it in meters. Say 200 meters, say 4% slope. The value of LS will be, for 4%, 0.56. Say for 100 meter slope length and 15% slope, the value would be 2.55. Similarly, we can use this table for determining the combined value of LS, provided you know the length as well as the steepness of the slope. Another factor is the crop management factor. This is again, I will repeat, this factor is under your one's management and under your control. If you have proper cover, soil cover, vegetation, if you practice proper tillage methods, if you use crop residue in your cultivation process, then the crop management factor would be less than 1. In fact, it is the ratio of soil from a land cropped under specified condition to the corresponding soil loss from tilled continuous fallow land. So it is a ratio between two things. One, there is one plot where all the specified condition of crop management is fulfilled, that is crop cover is there, proper tillage is there, cover crop is there, and all those good agronomic practices are followed. And second one, it is left fallow. This is where nothing is, there is no crop cover, no cover crop. So this is the ratio between these two. If there is, say there is no crop cover, if it is fallow, this factor value would be 1. And if it is covered with some soil, it would be definitely less than 1, means less less erosion, because soil erosion is directly proportional to C as well. So more the value of C, more will be the erosion from that particular place. And if it is fallow, the value is fallow and clean tilled land, then the value would be 1. That means land would be more susceptible to soil erosion. So this includes the effect of crop cover, crop sequences, tillage practice and residue management. These values are obtained from standard tables again. And the last component of this RK-LSCP universal soil loss equation is conservation practice factor, that is P. As we have discussed in the previous slide, conservation practice, again, what is conservation practice? We have also studied in land capability classification, where according to the classes of the land we have placed different control measures, be it agronomic, be it permanent, be it mechanical measures, according to the capability of the land, even in agricultural land. So this is again a ratio between two plots. One plot where the conservation, all the conservation or the required conservation practice according to its capability is made, and another field where there is no conservation practice. That is, if there is a certain amount of slope, or if it is a uniformly or gradually sloping land, we have not, in that such type of land, there is no conservation practice, no bunding, no terracing. And another one, it is properly, all the conservation practices has been followed according to the recommendation. So this is the ratio between these two type of land, that is the ratio of soil loss from land where conservation practice like contouring, strip cropping, bunding and terracing are followed, to that where they are not. So this value of P is taken as 1 if no conservation practice is followed, because this is a ratio between good and bad. Good divided by bad, it will be 1. So if there is no conservation practice, that means the value is 1. If 1 means 100%, that is it is allowing soil erosion, it is not controlling soil erosion. If we adopt conservation practice like bunding, terracing, then it will offer resistance to soil loss or water flow, thereby the factor would be something less than 1, depending upon the type of conservation practice and the reinforcement of agronomic measures that one is adopting. And this is again obtained from standard tables. So this is the one table which shows the C and P factor. Of course this is just indicative. Actual field condition things may vary, and it is for a particular land situation and for a particular country. So C and P factors for different land use, land cover is like this is vegetation, barren land, bushland, cultivation, forest, grassland, woodland, water bodies. The crop management factor C ranges from this to this depending upon different types of land uses, and this management factor also depends from 1 to vary from 1 to as low as 0.12 depending upon what type of management practices are followed. This is more clearer table. Here we have they have depicted the slope and also the crop management or conservation practice which are followed. In one case contouring is followed, other case contour plus strip cropping is followed, third terracing plus contouring both are followed. Say for particular slope type 1 to 2, 1.1 to 2%, if contouring alone is followed, then this value comes out to be 6. If contouring plus strip cropping means is followed, then the value is 0.3. And in such type of land slope, there is no question of terracing, because terracing we do terracing for higher slopes. So what does this value say? Tell me one thing, from which type of conservation practice land there would be more erosion? Definitely through this, because the value is higher, this is lower. Lower the value, lesser will be the soil erosion. Second, slope type 2 to 7% contouring. If contouring alone is followed, then 0.5 would be the crop management factor, and if contouring plus strip cropping is followed, it is 0.25. And in this case, if it is reinforced with terracing, then the value is even lesser. That means this type, for this particular type of land slope, if contouring is supplemented with terracing, then the value is even lesser. Similarly, for higher slopes, these are the different values. Let's do one problem based upon this universal soil loss equation. The problem goes like this. In an area subjected to soil erosion, the following information is available. Rainfall erosivity index is 200 megajoule mm per hectare hour. Soil erodibility index 0.34 ton hectare hour per hectare megajoule mm. So it's little confusing. This type of unit is coming just because of the interaction between this erosivity and erodibility. So this you have to remember, especially the units. This bracket will also come here. Length of the slope, that is L, is for that particular land in this problem in question is 60 meter. Steepness of the slope is 9%. Crop management factor C is 1. Conservation practice factor P is 1. That means there is no crop management practice properly followed. That's why the value is 1. And conservation practice factor P is also 1. That means there is no conservation practice being followed. Now, what will be the estimated annual soil loss? You have to determine through this USLE, universal soil loss equation, what would be the estimated annual soil loss, average annual soil loss in ton per hectare. And that is the first part of the question. In the second part, explain numerically how soil loss from this area changes if conservation practice measure of terracing plus contouring is adopted in this area. So here you are adopting terracing. In this second part, crop management factor, there is no crop, that is value is 1, but conservation practice factor we are changing through terracing and contouring. So how it will affect the soil loss from that area. Now using the solution, using the RKLSCP universal soil loss equation, R here is 200, K is 0.34. The combined effect of L and S, length of slope is given 60 meter, steepness of slope is 9 meter. Now what we have to do is we have to go to the table, standard table, where for a 60 meter length slope and 9% steep land, we have to find what is the combined topographic effect, or what is the topographical factor. We have to go back to the slide. Here you are. We will take this table. See our slope length, this is in feet. Our question is in meter. 60 feet will correspond to 60 into 3.3, around 200. So 200 is our slope of length, 200 feet, and our gradient or the slope is 9%. So this 9% will see 200 coming here. The value of this LS, that is the LS factor or the topographic factor, is 1.67. How did we find? We found out through this table, knowing the value of slope as well as length of slope. Coming back to the question again. Now we have found out 1.67. C, the value is given, and P is 1. C is 1, P is 1. Therefore, the soil loss A would be, this is a simple multiplication of R, K, L, S, all the factors. It is coming out to be 95 ton per hectare per year. Right. So, is it less or high? It is very high. Why it is very high? Because we are not adopting any conservation practice. There is no crop management here. That's why the value is, and also for the given slope and length of slope, this, and also the rainfall is also falling at very high energy, 200 megajoule per annum. For this high intensity of rainfall, the soil loss from that area for a particular year for that region would be 95 ton per hectare per year, in case there is no conservation practice or crop management. It's coming to the second part of the question, how the soil loss from the area changes if conservation practice, measure of practice, where if we as a part of conservation practice we include terracing and plus contouring in that area, then how this soil loss will change. Let's see. Here P is equal to, now we have to find the value of P through through table for 9% slope. So we again go back to the previous slides. Those tables are indicative. There would be a standard table that you have to refer for your condition, for your state, for your country. It would be for maybe for some other country. For just for explanation, I am showing you. So our slope is 9%. It comes under 7.1 to 12%, right? And what conservation practice we are adopting? We are adopting contouring plus terracing. For such type of conservation practice and this type of topography, the P factor is 0.12. So the value of P would be 0.12, where contouring and terracing is conservation practice is adopted for 9% of slope, which is our question, which is there in our question. So in such scenario, the R will remain same, K is same, LS is also same because length and steepness is same. C, there is no crop cover. Crop management we are not doing in that type of land. And P, the value of P we have found out is 0.12. Now the total soil loss will become A is equal to, if we multiply all these factors, it is coming out to be 13.62 ton per hectare per year. Now you just see and imagine, see this, you have calculated it practically, how a small factor, this conservation practice, a small intervention of contouring and terracing changes the soil loss. See, here it is 95, here is 13. Maybe 6 times the soil loss is lesser where you adopt such type of measures. So this is the importance of P, which this exemplify the importance of P factor as well as C. However, C crop management was not done, but still through conservation practice we were able to, this plot was able to reduce soil erosion by 6 times. So in India, soil losses has been classified into 6 different categories: slight, moderate, high, very high, severe and very severe. And they have defined the erosion rate as 0.025 to more than 80 ton per hectare per year in these categories. In very high, if it is 20 to 40, it comes under very high. If it is 10 to 20 ton per hectare per year, it comes under high. And there is also data for the entire our country. So the total area which is slightly affected by soil erosion is 8.01 lakh square kilometers, and moderately affected is around 14 lakh square kilometers. So this way you can go through this table and have a rough idea how much is the extent of soil erosion in different parts and its acreage in terms of area. There are certain limitations of soil erosion, universal soil loss equations. First limitation is it is empirical, it is not based upon field data. It is based upon field experiment. It's a it's based upon modeling or runoff simulators of a particular field, and it has been compared with some standard fields. Then we have come to the soil loss equation. It's not actual, it's a empirical. That's one limitation. In actual field condition, the soil loss may differ. There we have to go for this PEG methods or sedimentation tank method, or simply the simulator plot method for the individual field. Second is this is the average annual quantification. Through this equation we cannot say for a particular rainfall this much of soil loss is happening. This is average over a period of many years. So we can have an estimation for annual soil loss, not for a particular period, for a particular duration of storm or a particular area. There is another limitation. Third is it does not control gully erosion. We have studied in the previous classes that gully erosion is one of the major form of soil erosion where large amount of erosion takes place. But here we have considered only the agricultural land where mostly raindrop erosion, rill erosion and sheet erosion takes place. That gully erosion is not considered through this universal soil loss equation. And lastly, last limitation is it also it neglects the sediment deposition, because in large structures there is, due to flowing of water, large amount of sediment there is not only losses, there are also some deposition of soil in certain place, because soil erosion is detachment, transportation and deposition, and this deposition we do not consider in this universal soil loss equation. These are some of the limitations of soil loss, universal soil loss equation. Still, over the last 50-60 years, there is any mathematical model as popular as universal soil loss equation, and this is very widely used in India, all over the world, for estimation of soil loss, for predicting the soil loss over a large area. And also this method is also used for deriving many other formulas. So that's all from my side today. So see you next time. Thank you.